Let's concentrate now on the idea of line integrals through vector fields and just what exactly these things are going to mean. Now, suppose that you're in a kayak on a river and you have a noticeable current. So there's some type of current that you can actually feel. At times you may be paddling generally with the current. At times you may be orthogonal to the current. At times you may be totally against the current. The idea between a line integral through a vector field is going to measure the extent that your path of travel is with the current or with the vector field. So let's go back to the kayak idea. You have this river. So you have this vector field that represents the current in the river. Clearly, where it narrows out, the magnitude is going to be much greater. And then out here is going to be much smaller. And then here you are bebopping down along the river, and you dropped your hat, so you had to go back and get it. Now, if you think of your orientation here, clearly throughout this area, you're pretty much going with the current. Over here, you're kind of orthogonal to it. Now you're directly against it, going totally opposite direction. Here you're somewhere in between, and then you grab your hat and you pick up and take off with the current again. So you're back in a general direction with the current in that case. Now, when we're talking about this idea here of the extent your path of travel is with the current or traveling with the vector field, we can use this idea and cite an example for a line integral through a vector field. And what it does, it gives us a way to measure the amount of work done along a curve through a force field. So if this vector field is a force field, like a gravitational force field, it can line integral would tell us the amount of work done traveling along that path through that force field. Now, before we get too deep into this, let's start talking again, or remind ourselves quickly on what we mean by an oriented curve. If I have a point P and a point Q, point Q, and I travel from P to Q, this curve is not orientated. It doesn't give any indication of what the actual travel was. All I have is something connecting P and Q. Now, on the other hand, if I go from P to Q, and I stick that little arrow on there, or if I go from Q to P and have this arrow on there, both of these are in fact orientated curves. It tells us our direction of travel. Orientation is extremely important when we start thinking about the idea of a line integral through a vector curve. I'm sorry, a line integral through a vector field. Okay, so here's the basic idea behind line integrals through vector fields. First, let's recall that we first introduced the idea of a dot product as a calculation for the amount of work that was done moving an object with a specified constant force F along a displacement vector D. So I have this constant force F, and I'm moving from point P to Q, which I'm representing as this displacement vector. Now, suppose that this force vector F can be represented as Pi plus Qj plus Rk, and that this is continuous. Or is a continuous force field. In 3 space. I should say A, is a continuous force field in 3 space. As example, this could be like a gravitational field. Now, let's draw this out a little bit here. let's say I have some initial point, I'm going to call it P naught, and I have this curve that comes around to this point, say Pn, which is point Q, and I have all these points along the way. Now, so let's say this point right here is point Pi. That would make this point Pi minus 1. So if I divide this into, see, each piece here I'm thinking as a subarc. If I divide this into small enough subarcs, then actually the direction of movement from Pi minus 1 to Pi is very well approximated by the tangent vector T of Ti star, where what I'm really thinking about here is some point along here I'm going to call Pi star, which is just something in between, or some point between Pi and Pi minus 1, and it's going to have coordinates xi star, yi star, zi star. Sorry, I got kind of close there. So it's just some arbitrary point somewhere in here between the point Pi and point Pi minus 1. And this tangent vector here was going to be tangent to that point. Now let's say that my force field at this point, say it looks like this. So this is going to be F of xi star, yi star, zi star. So what I'm claiming is the direction of travel along this subarc, if this subarc is small enough, is well approximated by the tangent at this point, which would be this vector right here. So I can think of the amount of work done from Pi minus 1 to Pi to be approximately equal to this, the force field, or the force vector at this point, xi star, yi star, zi star, dot this tangent vector delta S, where delta S is just the arc length. So if I look at the total work done, I can take a look at the limit as n goes to infinity of the sum I equals 1 to n of this vector function f, xi star, yi star, zi star, dot the tangent vector at ti star, delta s. So I have this dot product, which is basically you can think of as the amount of work done with this force vector it moving in this direction, and this delta s is actually the arc length, is how far that we're moving. And actually I should make that delta s a delta si, and this is my x axes here. But in the limit, we recognize this as simply being the integral over the curve of f dot t, where here's f and here's t, and delta s is ds. Now, this is actually a form of the line integral that we can actually work with. Now, recall that the unit tangent vector t equals r prime of t over the magnitude of r prime of t. And we already looked at the idea that ds equals the magnitude of r prime of t dt. Remember, ds dt is r prime of t, so ds equals r prime of t, or the magnitude r prime of t dt. Therefore, we have the integral from a to b of f of r of t dot t, but t is r prime of t, magnitude of r prime of t, ds, but ds is the magnitude of r prime of t dt. So those will just cancel out, which gives us the integral from a to b of f of r of t dot r prime of t dt. And let's keep up here. This is one form. This is yet another form. But remember, r prime of t equals dr dt. So if I substitute that in, I'll have the integral from a to b of f of r of t dot r prime of t dt. But if I substitute this in right here, then it's going to look like the integral from a to b of f r of t dr dt dt. Those cancel out, and then you'll see another form that this is very commonly written in, that being the integral from a to b of f dot dr. So here is yet another form. It's an abbreviated form to represent the same line integral, and this guy is identical to this guy, which is the same as this guy. So, bringing this all together in a definition, let f be a continuous vector field on a smooth curve C by a vector function r of t, where t goes from a to b. Then the line integral of f along C is the line integral of the vector field along this path C is given by the integral along the curve, on the path of the curve C, of f dot dr, and that is also equal to the integral from a to b of f of r of t dot r prime of t dt, which is equal to the integral along the path of that curve of f dot t ds. So this is just a recap of those three different forms that I just pointed out to you and I actually just derived. They all mean exactly the same thing. It just depends on what you're working with. One might be a little bit easier to work with than the other. But again, keep in mind, they all actually represent, they mean the same thing.